In this video, we'll talk about cycle detection in a directed graph using graph coloring method. So in the last video, we saw there are two ways to detect a cycle in a directed graph. So one is using DFS and the second one is using graph coloring method. Even in the graph coloring method, we use depth first search traversal. But the difference between the first method and the second method is in the first method we use recursive stack, but in the second method we use colors to identify vertices. Now let's see the procedure of graph coloring method, post which we can compare the differences between the first and the second method. So this is a sample directed graph in which a cycle is present. How can you detect a cycle? Basically, if you start from your vertex and if you reach the same vertex while traversing, then we can say that there exists a cycle. So if you see here, I can go from B to C, from C I can go to E, from E I can go to D, and from D I can go to B. So there exists a path through which you can reach B again. So that's why we can say that there exists a cycle in this graph. And now let's see the process of detection using graph coloring. So in the graph coloring, so as the name says, colors. So we use three colors to identify to name vertices. Okay. So the three colors are white, gray and black. So our vertices in the graph falls either one of these three colors. So at any time, each vertex is assigned one of these three colors. So when white is assigned, when gray is assigned. So that is as per this logic I have written here. So if your vertex is not visited, then the color of the vertex is white. If the vertex is visited, but we have not processed its descendants or its neighbors, then it is gray. Means in process vertex is called gray. Let's say now I started from A, okay. Now I visit, when I start from A, which means that it is visited. But I have not processed its neighbors. Then initially my vertex would be white. When I start processing it, I visit A, right? So when I visit, it will move to gray. And since all its neighbors are not processed, the color of this vertex would be gray. Now I go to B. Okay. When I go to B and I process B neighbors completely, and when I come back to A saying that I have processed all your neighbors, then color of A will change to black. So basically here a white is a vertex which is not visited. Gray is a vertex which is visited, but its neighbors are not visited. Okay. So when let's say you take a vertex A or B, if a vertex neighbors are all processed, then we can say that B is completely visited and processed. Okay. So three things: visited but not processed, and then visited and processed. Not initially all vertices will be white because we have not visited any of the vertices. When we start visiting visiting vertices, the vertex will move to gray, and when all its neighbors of the vertex gets explode, then the vertex will move to black. So this is what I have written here. White is not visited, gray is visited, but it's not processed. Not processed means its neighbors are not yet explode. So if I say, if the gray means it's visited but its neighbors are not yet explored. If all neighbors of A are explored, then I can say that A is completely processed. A processed node is a node in which all its neighbors are explored, including the vertex. Okay. Yeah. Now let's start doing this. So initially I'll start with A. Okay. So A is not yet visited. A, the color of A is white, okay, which means that it's not visited. So what I'll do is I'll move the color of A to gray. Now here it is white, right? So color should come gray. I'm just putting it as G. You can assume that as a gray color. Now see the neighbors of A. What is the neighbor of A? It is B. So is B visited? No. What is the color of B? White. So it is not visited. So what I'll do is I'll move it to G because I visited it but I have not yet processed it. Now from B, what is the neighbor of B? C. Okay, now see the color of C. Oh, C color is white, which means it is not visited. Okay, I'll visit it. I'll visit and I'll mark it as a gray. Okay, now from C, you go to E. The neighbor of C is E. So E is white, which means it's not visited. So I visit E. So whenever I go, I'm marking as this visited. I go to E and then I'll make this as a visited, which means I'm making this as gray. From E, what I'll do is I'll go to, there are two neighbors, okay? One is D and one is F. If you see the color of D, it is white, and if you see the color of F, it is white, which means both are not visited. I can choose any one of those vertices, okay? Now, instead of choosing D, I'll choose F, okay? When I go to F, I'll change the color to gray, okay? Now from F, is there a way to go? No, it is dead end. So what I have to do? I have to trace back the path. When I trace back the path, which means that F is completely processed. So when I put 2 marks here, it is completely processed. So when it is processed, what I'll do? I'll move the color from gray to black. Okay. Now from E, from F I went back to E. From are there any other vertices which are of white color? Yes. If you see, D is the another neighbor. So you just have to explore your neighbors, okay? So from E, you have another neighbor D. And if you see the color of D, it is white. Okay, I'll move it to G. Now, from D, what are the neighbors from D? B is the only neighbor. What is the color of B? It is gray, which means it is visited but not processed. So if you the condition comes like this, where you encounter a vertex which is of color gray, which means which is visited and not processed, then you can say that there exists a cycle. So the condition for cycle here is when you are doing a traversal, basically when you are doing a DFS traversal, when you encounter a vertex which is visited but not processed, then we can say that there exists a cycle. Because you can encounter a vertex, you basically process a vertices which are not visited. If you if it is not visited, then you will visit that vertex and from there you will continue your traversal. But if you encounter vertices of gray and black, if you encounter black vertex, then also it's fine because it is visited and it's completely processed. You need not do the rework again. It's a duplicate work. But if you encounter a gray vertex, then it means that there exists a cycle. If you see here, from B, you went to C, you went to E, you went to F, but you came back because there is no path. Then from E, you went to D. From D, you went to B. So which means there exists a cycle. So this is the condition for detection of a cycle using graph coloring method. Basically, this is the, normal process to follow. But if you think it visually, okay, so I start from B, then I go. So if I encounter a vertex which is not processed and visited, then simply you can say that there exists a cycle. And if you compare the difference between the first method and the second method, so basically, if you think deeper, both are actually the same. The only difference is here we have assigned colors to the vertices, but both traversals are same. You have used DFS traversal in both methods, but the only difference is instead there you took a recursive stack to see the vertices which are visited and not processed. Here what you have done is you have used coloring method to find out the vertices which are visited but not yet processed. That is the only difference. There the stack is used, here the colors are used. Apart from that, both are same. And if you talk about the time complexity of this, here what are we doing? You are visiting each and every vertex and each and every edge. So the time complexity would be order of V plus C because each and every vertex and each and every edge are getting visited. Okay, this is the time complexity. And if you see the space complexity, anyway, for DFS traversal, we are using stack. Because for, like if you see here, when you went to E, you have two neighbors. One is F and one is D. So you are in DFS, in a regular DFS traversal, you use a stack, right? Because you explore only one vertex and the other vertex won't be explored. So generally stack is used for DFS traversal. If you can exclude, like if you exclude the stack, the space you have used is to store these vertices colors. So order of V is the space complexity. So in terms of space complexity, if you see clearly, I am excluding the stack. So that stack can be like if you code a problem, so either you can explicitly specify a stack and then use that for your DFS traversal, or you can use recursion method in which it comes as a recursive stack. So if you exclude that recursive stack, the time complexity, the space complexity is order of phi. So the time and space complexities are same for both the first method, DFS using recursive stack, and the DFS using the coloring method. Yeah. In the next video, we talk about detection of cycle in undirected graphs. Thank you.